Yo! So welcome to my presentation about securing the open source supply chain. My name is Morten Linderud, and we'll talk a little bit about how we can secure the sort of the open source supply chain, how we can procure sources and sort of deliver them to your machine, and how the sort of the ecosystem is sort of developing and adapting to the new challenges. So my name is Morten Linderud. I go by the nickname of Foxbaron on the internet. I work as a security engineer at Defendable, where I sort of do log pipeline stuff. I have a master degree from the University of Bergen, where I wrote about supply chain security and Debian specifically. I've been a FOSS developer / maintainer since around 2013, and I've been an Arch Linux contributor since around 2016, where I mostly do sort of security team stuff, managing CVEs, and publishing advisories, Reproducible Builds, which we'll talk a little bit about later, and then also a lot of packaging with different software. So, quick disclaimer, this talk doesn't necessarily represent the views of my employer, etc. This is also sort of a short talk, so it might not necessarily be super detailed on some of the specifics, but it's still sort of an attempt at wrapping up a lot of the disparate topics. So the first thing we'll take a look at is reproducible builds. And reproducible builds is sort of a little bit of the foundation that we'll build a lot of these rest of the building blocks on, because it's essentially sort of a set of software development practices that create an independently verifiable path from source to binary code. What that means is that it essentially tries to sort of figure out how do we take out all of the variables from a compilation build of code and make it reproducible, so we can bit for bit verify the different binary distributions of said file. To sort of illustrate how this works in practice, I have made some SVGs of how packaging works. So we have me, and I sort of went through all of the different packages I maintain, and I realized the most popular one was the Go compiler. So when we package a new version of Go, you sort of have to figure out where these artifacts are published. In Google's case, all of them are on storage.googleapis.com. So when there's a new version, the tarballs are uploaded to that location, and it usually contains a signature. And this is sort of what we use to build a package. What we do fetch out of bound is the Google package signing key. And it's sort of important that this does not arrive from the same location, because then the distribution mirror could be compromised. So having this out of bound fetched from another location and then verify the source tarballs ensures that we can trust this release. Then I can publish this up to a build server, which is going to take the source code, turn it into binary. And at this point, I can go and say, I made this. And now how to sort of give it to the world as well. So I take the sort of newly built package, and I upload it to the tier 0 mirror, which is where we sort of do all of the package distributions. The packaging mirrors are going to fetch all of the packages from the tier 0 mirror, and these packaging mirrors is where you get your software updates. And it could be your computer, it could be your servers or containers, and so on. Reproducible builds essentially ensures that I haven't messed with the code, the build server has not messed with the code, and the tier 0 mirror has not messed with the code, by ensuring that they can actually fetch the source code, compile the package that I built, and get an identical built package. So this is sort of complicated, and you might be wondering how well it works in practice, like in a real-world situation. And that actually is a little bit funny, a little bit amazing, but in Arch we have 85% of 12,000 packages reproducible, which is a good number. It fluctuates a little bit between 87 and 81, depending on the regression we find, because we break stuff. I think it's at 80% now because I haven't patched our tooling yet, and there's a regression, so I had to fix that. It's how this translates to a live system is that I can ask what the reproducibility of my system is in terms of packages. And you'll see that I have a 93% reproducible system. And that's amazing. Like, sure, yay, supply chain secured. We don't have any issues at all because we'll soon reach 100% and everything is going to be amazing. But that's not really true because Reproducible Builds only really cares about the distribution network that we created. Is there any other vector that could sort of sneak in code? And the answer to that is that we don't really have any clue what was necessarily pushed from the Google storage. They signed some tarball from their source code repository, but we haven't, they could be a million commits in their project. We have no clue what was done to it. So the real question sort of entails though is, what about source code? How do we secure the source code that we depend on for these sort of things? So in 2011, kernelorg, which hosts the Linux kernel source code and a few other projects, was hacked. They didn't find any modifications, but yeah, and this was the second time, I think, which was compromised. In 2018, the Gentoo Linux distribution got their GitHub organization hacked because they did not have two-factor authentication on one of their developers. And those people actually tried to modify packaging files. It was obviously stopped and two-factor authentication was later added. But it's a little bit worrying when sort of the holy grail of Linux distributions are attacked and compromised in that way. Another good example is NPM, like in general, like there's I don't know, 100 different cases, something with tarballs being swapped around and fetching your Bitcoin wallet, sending that off to somewhere, or compromising your build, or those sort of compromises. But to sort of exemplify a recent scenario, the PHP Git repository was compromised fairly recently. And it's a little bit interesting how that sort of attack vector is done, essentially. So this quick disclaimer, I don't actually know what was done. I just did a little bit of guesswork based on experience, and I just hope it covers the scenario as an example. So you have Rasmus Lerdorf, which was the main creator of PHP. When he sort of interacts with the Git repositories, he usually does that with the git.php.net server, which is where the PHP source bare repository is located. This is then sort of a mirror over to the GitHub repository, and this is sort of the two locations where people fetch the source code for really sort of development builds, patches, and so on. The releases to PHP is done on a separate server called php.net, and I don't know how they do the releases, probably rsync or something. But these tarballs are protected by reproducible builds because if something happens on a distribution server, you can still check out the source code of the Git repository and compare it, and you'll figure out that it does not add up at all. But so that's sort of covered, but in the PHP scenario, you have a hacker, in this case, ZeroCool, which did actually manage to get physical access to the server and sort of inject malicious code into the bare repository. And it was a little bit, I think we called it a little bit amateurish because it was detected. It's not super obvious, but you see the revert of a revert skips CI fixed typo. This reverts some commit, but it also adds a fair big blob of code, which fetches something from HTTP header and then tries to execute that. So this was detected and reverted, and everything is fine. They also sort of migrated away from their private server, which was poorly maintained, over to GitHub, which is hopefully more secure. But they still didn't really figure out where this code came from. They just assumed it was a physical access, and they don't have no traces of who put the code there. So what can we do to protect against these issues? So a feature that I've honestly recently learned about is that Git push can actually do certificates or attestations of what was uploaded. So git push -- sign sort of tells the server that I want to sign. I upload a bunch of stuff to you, and I want to sign that I did upload this stuff. And that allows us to sort of make a statement about this is what I did, and you can verify that I pushed this code. And the way this works in Git is that git push -- signed sort of initiates this connection. You have the standard git commit, and from this commit, it generates a sort of attestation saying this key at this timestamp pushed this repository, and then a nonce because it needs to be unique, and then the sort of the commits to this repository. And you see I pushed from the root commit 0000 to this new commit. I pushed to the master branch. Following this certificate is a signature that I made saying I did this, and this is sort of the gist of it. It also then completes the rest of the transaction. But this isn't super useful on its own, because if this was only done on PHP's side, I would not necessarily know about this attestation, and I would have no idea how to verify them. And PHP does not do this. I don't think GitHub has support for it either, but people hosting their own stuff have implemented it. And an example of this is kernelorg, which I mentioned earlier was compromised in 2011. And they actually push all of their sort of git push operations to one Git repository, so you can go and view them and actually see what's being pushed. But I'm not sure how do you review this? Like, how do you actually look at the commits and go say, yeah, this looks fine, or distinguish it from a malicious commit to this repository? Because it's still the same server as the rest of the source code. So if you look at each file, you'll essentially just see email, which just contains all of the files, and good luck trying to eyeball whatever this is supposed to mean. So the real question is then, how do we monitor this at all? Like, do we just git clone it and sort of figure out on our own how this works? So after I sort of submitted this talk, I realized it would be a fun project to try write a monitor for this service, so I did. So this is a kernel.org transparency log monitor, which I wrote as a sort of a weekend hack earlier this month. And it essentially just checks out the Git repo you just saw, and just verifies all of the different commits with the signatures. So you see Greg, very good at signing all his pushes. The other people, not so much. And Greg is the Linux stable kernel maintainer, if you don't know. And this is just an example of how it could look like. There's a few features missing, sort of things like, can we check if all the commits in a kernel release is witnessed by this log, and can we verify all of it? A little bit open question, but this is sort of a little bit fun to hack around with. So this was just sort of a weekend hack just to see if I could do it. But this is pretty much just a thing that's unique to the kernel. Like, nobody else is publishing a log like this, so it's a unique format. It's specific to the kernel community, and that monitor is probably not going to be useful for anyone else except for the kernel. So what about the rest of us? Like, my pet projects, I like if I could have some verifiability of the commits that's done to them. Other people might have some interesting projects that they want to have on this log, but they don't necessarily want to host a log like that and depend on other people sort of monitoring that log. So this is what is sort of a new project from Linux Foundation. It's a project called Sigstor, and it does essentially what you think it does. And it allows you to take release artifacts or git push certificates and append them to a transparency log, a public one at that. This is a Linux Foundation project. It's worked on by people from Google, Red Hat, Purdue University mostly, and a few others. And it's a public transparency log for signing objects. And the strength in this is that there's one place to store all of it, and preferably in abstract ways, so it's reusable as well. And this is similar to what you probably recognize as certificate transparency. And it's essentially a way to have tamper-evident logging of things that's being signed. And this, you can witness this log, ensure all the releases are on this log, or you can fetch releases from Google and how to verify that it's all on that log. But we still need to sign stuff. And I mean, first of all, like GNU-PG is terrible. I use it a lot. It's completely terrible. It's hard to use. So if we don't want to use GNU-PG to sign stuff, we need more stuff to sign or other things to sign with. So what Sigstory is trying to experiment a little bit with is about OpenID Connect identities and create certificates from them to sign release artifacts. And this sort of, it makes it a little bit of a possibly a silo because Sigstory does their own thing, but it enables regular maintainers to better sign their objects with their own identity instead of having to rely on some extremely poor tooling like GNU-PG for regular developers. So we then have OpenID Connect certificates, and we can sign releases, and that enables us, as mentioned, to ensure that all the releases we want to have is on this log. And it also is sort of a better way for us to ensure that things are secure from A to B, because now we can have more security built around our Git repositories. And because it uses OpenID Connect identities, it's a sort of a public web key infrastructure, or web PKI, I saw somebody call it. And it's sort of what Keybase tried to be a few years back, but it's still dependent on GNU-PG, which is not a good idea in 2021. So it's probably a better idea for some people to look at instead. But what should we be signing then? And this is sort of the fun thing about this project, is that it's not dependent on one thing. They implemented cosign, which is capable of signing Helm charts, containers, OCE images in general. I know people use it for Kubernetes as well, I believe. And that enables you to sign things, append them to this public log, and then you can sort of verify it. And this is not constrained to sort of OCE, the OCE format, but it's one example of the format you could implement. And how this is actually implemented is JSON records, which are implemented different types, are appended to this tree, which is then checksummed and then checksummed upwards. Similar to blockchain, without the baggage and the consensus algorithms, it's just a tree with checksums. And because checksums are secure, we can always know if a tree is consistent or not. So this sort of has not implemented all of it, it's still a work in progress. The web PKI stuff is not properly implemented yet. But I think this, like I showed off my current transparency logging project, and I think this is probably a good target for that as well. So that's sort of on my to-do list to try and implement. So somewhat in conclusion, open source is adapting. We do actually get new, like Reproducible Builds and sigistor is great projects, which enables us to have a more secure supply chain for open source projects. Reproducible Builds ensures that the distribution network of these packages or the build systems can be verified. And then transparency logs ensures that the releases and the Git commits potentially of the projects are all tamper evident. And this sort of improves the provenance of our system because we can then sort of take our container, we can deconstruct the container, verify all the packages in that container, reproduce them, and then also trace all of that hopefully back to a transparency log and see that the commits have been verified. And that sort of gives us the complete history of the projects. But it's sort of like a dark side to the story, and that's we need to fund open source work because Reproducible Builds is headed by 2 or 3 people. Most, like, there's 10 other regulars, all of them volunteers doing this in the free time. Sigistor is a few companies putting in a few resources, but it's not like a huge team. So it's sort of back to this XKCD image, which was done earlier this year, which is a joke, but it's depressingly true at the same time. That a lot of these infrastructures are dependent on extremely few people, and there's not a lot of money that goes into these projects. So it shouldn't come as a huge surprise when the registrar writes that much of the open source world is critically underfunded, yet critically important, because that's sort of the situation we have gone ourselves into. So what can we do to solve this? And that's to fund people. The problem is that in the capitalistic system, people care about their bottom line and earning money, and that's not sort of one-to-one with we should fund idealists that works on this on their own free time without necessarily earning any money on it. So what can you do as a privileged developer? You can push your workplace to fund people working on this project, or dedicate some developer time to this project to help out because it's sorely needed, and it's extremely important to secure the open source infrastructure. If you can't get your work on board, you can donate yourself. I do. So GitHub sponsors, lovely project. I sponsor Florian Brunnen, which writes my web browser that I use. Daniel Stenberg is the curl developer, a Swedish guy. If you don't know what curl is, it's literally running everywhere. Phone, your watch, your TV over there probably runs curl. It's essentially what everybody uses to fetch network resources. Jason Donfeld, who writes WireGuard, which should be no stranger to most technical people. And there's not a lot of money donated, but collectively it's a lot. So that's sort of the main takeaways, that open source has solutions, but there's essentially not enough people working on all of these solutions. So that's pretty much my talk. I hope it was somewhat insightful with a few twists and turns. I have a Twitter if you're interested in discussing with me. I also have a GitHub as Foxboron. I also have an email if you want to email me and discuss. I also have a blog with stuff I do on my free time in terms of open source development. Yes, thank you for having me. Thank you for your time. I think there should be a Q&A session starting soon, and have a lovely conference going onwards. Thank you.